Welcome to this explainer. If you've ever interacted with a cutting-edge AI and just felt a little shiver down your spine because it sounded, well, a little too human, you definitely aren't alone. It's so easy to look at these massive data centers and their astonishing capabilities and assume there's some kind of digital consciousness hiding in there. But the reality is actually much more grounded, and honestly, I think it's way more fascinating. Today we're jumping straight into the mathematical engine that actually powers modern artificial intelligence. We're going to strip away all that sci-fi mystique and look at the real gears turning under the hood.
Look, let's just get right into this because there's a huge misconception out there about how these systems operate. When people hear artificial intelligence, they almost always picture this glowing synthetic brain making conscious decisions. But AI models aren't magic. They really don't think the way you or I do. In reality, they're just incredibly powerful, highly optimized math engines, and their entire existence is dedicated to one single obsessive goal, constantly searching for the lowest possible mathematical error.
So here is how we're breaking it down today. First, the math behind AI learning. Second, measuring mistakes with loss functions. Third, navigating the foggy mountain. Fourth, the chain rule connection. And finally, backpropagation and modern AI.
All right, let's kick things off with Section 1, the math behind AI learning.
Let's start by grabbing our fundamental gear so we can really understand the basic building blocks of any machine learning model. And it all begins with a function. At its core, an AI model relies on multivariable functions. Picture a model tasked with predicting real estate prices. It maps specific inputs, say a home's square footage, the number of bedrooms, and maybe a location score, to a unique output, which is your final estimated price. So if you've got a 2,000 square foot house with 3 beds right downtown, the function crunches those variables and spits out a dollar amount. Now, I want you to take that concept and scale it up to an almost unimaginable degree. Modern neural networks take in millions, sometimes literally billions, of these data points just to generate a single output prediction.
But here's the million-dollar question. How do we know if changing one of those inputs makes our final prediction better or worse? Well, for that, we use derivatives. To get how derivatives work, just think about checking your car's speedometer. A derivative basically just measures how quickly something is changing. If you have a small derivative, that's a slow change, like your car just cruising slowly through a neighborhood. But a large derivative, that means rapid, volatile change, like your car rocketing down the highway at high velocity. In machine learning, derivatives simply tell the model how fast its prediction error is going to change when its internal parameters shift. And you absolutely want your model to know if its mathematical speedometer is going dangerously fast in the wrong direction.
Now, because neural networks contain billions of parameters, calculating a simple, single derivative just isn't going to cut it. We need partial derivatives. Imagine looking at a super detailed temperature map of a massive city. Partial derivatives let us compute the slope in one specific direction at a time. It's exactly like measuring how the temperature changes when you travel strictly east to west entirely independently from how it changes if you were to travel north to south. Scale this up to AI, and it is truly mind-boggling. A modern computer is simultaneously computing partial derivatives for billions of directions at once. This is absolutely essential because it tells the system exactly which specific parameter, out of billions, most directly affects the current prediction error.
Moving right along to Section 2, measuring mistakes with loss functions.
Now that we've got our math tools, we need a way to figure out how far off our model's predictions actually are. Think of the loss function as an incredibly strict, aggressive teacher grading a final exam. It's a formal, non-negative mathematical measure of exactly how wrong a model is at any given moment. If the model guesses a house is worth $1 million and it actually sold for $200,000, the loss function slaps it with a terrible, massive score. So the crucial takeaway here is that these models are inherently lazy. They absolutely hate high numbers. Learning or training a model simply means relentlessly searching for the internal parameters that make this wrongness number as close to zero as mathematically possible.
And depending on the specific problem you're trying to solve, you're going to need a different mathematical compass. If you're predicting a continuous number, like that house price or tomorrow's temperature, you generally use mean squared error. This formula is notoriously aggressive. It actively punishes large outliers by squaring the error, which forces the model to fix its biggest mistakes first. But what if you're categorizing things? Say, deciding whether an incoming email is just a harmless newsletter or a malicious phishing scam. For that, we use cross-entropy. This concept actually comes from information theory, and it measures how surprised the model is by the actual truth.
If the model was 99% confident an email was spam, but it turned out to be from your boss, the cross-entropy loss would absolutely skyrocket because of that high level of surprise.
Which brings us to Section 3, Navigating the Foggy Mountain.
Okay, so with our loss calculated, we are finally ready to begin the physical descent towards zero error. To do this, we use an optimization algorithm called gradient descent. I want you to imagine you're standing high up on a rugged mountain. But there's a catch here. You are completely blindfolded, and a thick fog surrounds you. You have literally no idea where the bottom of the valley is. All you can do is physically feel the slope of the ground directly beneath your feet. The gradient vector mathematically combines all our partial derivatives and points uphill. So to find your way to the valley of zero error, you just follow the negative gradient. It points in the steepest downhill direction, showing your model exactly where to step next to intuitively reduce its error.
This creates an elegant, highly repetitive three-step loop. Step 1, you calculate the gradient to find the slope's steepness and that all-important downward direction. Step 2, you take a literal mathematical step down the mountain by updating your weights. And Step 3, you repeat, again and again. The model constantly reevaluates its precise position, feels the slope of the ground, and takes another step downward. It does this thousands, sometimes millions of times, until the ground finally flattens out, meaning it has successfully reached the valley of lowest possible error.
But wait, there's a major catch here. The size of those mathematical steps is controlled by a setting called the learning rate. If your learning rate is set too small, your model takes tiny, hesitant baby steps. I mean, it'll eventually reach the bottom, but it results in agonizingly slow learning that wastes a ton of computing time. On the flip side, if your learning rate is too large, your model takes massive, reckless leaps. This causes highly unstable learning. The model might actually bounce violently off the canyon walls, completely ruin hours of expensive compute time, and entirely overshoot the valley. So choosing the perfectly balanced step size is totally critical to ensure a smooth, efficient convergence to the bottom of the mountain.
All right, let's look at Section 4, the chain rule connection. Everything we've discussed so far makes perfect sense for a simple equation. But how in the world do we calculate these gradient steps when the mathematical path in a modern neural network has dozens, sometimes even hundreds, of complex, overlapping layers? To understand how errors propagate through these deeply complex networks, let's look at a relatable, real-world dependency chain. Let's invent a character. We'll call him Bob. Bob's salary directly affects his daily stress levels, and those stress levels, in turn, heavily affect Bob's long-term health outcomes. Therefore, Bob's salary indirectly affects his health outcomes through an intermediary layer, which in this case is his stress.
What makes this so fascinating is that the final outcome depends entirely on the specific direction of the relationship at every single link in the chain. Think about it. Does making more money always improve health? Well, if Bob gets a raise, that higher salary could reduce his financial anxiety, which lowers his stress and ultimately improves his health. But what if Bob takes a high-pressure, incredibly demanding executive job to get that high salary? That vastly increases his daily stress, which then absolutely destroys his health. The positive or negative signs of each individual link can completely flip the entire final outcome.
And this is exactly where the chain rule comes into play. It's a foundational calculus formula that elegantly combines these indirect cascading effects. It tells us that when functions feed into one another, like links in a chain, we can compute the final, overall change simply by multiplying the mathematical links in the chain together. It allows us to pinpoint the exact final impact of an initial input on the ultimate output, no matter how many complicated layers or intermediary variables lie between them.
Let's wrap it up with Section 5, backpropagation and modern AI.
Let's connect all of this foundational math back to the massive neural networks that are actively reshaping our world today. In deep learning, the chain rule is the driving force behind a concept called backpropagation. This is simply the repeated application of the chain rule, moving backward through a computational graph. Think back to our strict teacher grading a test. Backpropagation is like that teacher not just putting a massive red F on the paper, but painstakingly tracing backward through the student's work to identify exactly which specific math mistake on line 2 caused the final answer to be wrong. Because it propagates the error backward from right to left, backpropagation enables the entire complex system to learn exactly which specific weights to increase and which to decrease to get a better score next time. And this exact process of calculating gradients, stepping down the foggy mountain, and optimizing loss functions is the very engine running behind the most advanced technologies in our daily lives. When Netflix's recommendation system suggests your next favorite movie, it's constantly calculating prediction errors and updating its parameters. When a self-driving car successfully detects a lane and predicts the motion of a pedestrian, it is relying on these exact neural networks. And when a system like ChatGPT writes a poem or answers a complex coding question,
It is performing billions of these little mountain-stepping calculus equations behind the scenes, leveraging enormous text data sets to optimize its language predictions. The sheer awe-inspiring scale of it is what makes it feel like absolute magic.
So ultimately, what seems like mysterious science fiction artificial intelligence is actually just an incredibly vast, beautiful application of foundational calculus. Calculus gives machine learning models the fundamental ability to learn from their errors and continually improve their predictions through the power of optimization. It is, quite literally, the mathematics of learning from mistakes. Thank you for joining me on this explainer. We've journeyed from basic functions, down the foggy mountain of gradient descent, all the way through the cascading links of backpropagation. I'm going to leave you with this final, thought-provoking question to ponder. If calculus allows artificial models to learn from their mistakes by ruthlessly and coldly seeking the lowest point of error, what happens when we start asking these mathematical systems to optimize incredibly complex, highly nuanced human behaviors? And how do we even begin to define the perfect loss function for the messiness of the real world? Keep learning, stay curious, and I will catch you in the next explainer.